Kia ora, welcome to video 8 in the series Insightful Integration. In this video, we're going to look at the volume formed by rotating an area around an axis. If you're not familiar with volumes of revolution, then you probably should study that up first. It's just an integral formula, but if you've never seen it, it can be a little bit tricky to derive on your own. We've got a curve that involves a hyperbolic cosine function, but you're also given there the definition of that. It's just the sum of two exponential expressions, divided by 2. So finding the volume of this, once you've got the integral formula, it's just a matter of integrating the right thing. It can get a bit messy though, because this thing here is going to have to be squared in the integral formula. Anyways, all the best, and we'll catch you for the solution after the intro music.
Alrighty, so volumes used to be a part of NCA integration, and then they removed it from a standard. If you were going to get given a problem involving volumes like this one, you would get given the formula, the integral formula for volume. There are different types of formula, but the one for rotation around an axis, the formula is pi integral between the limits, in this case 0 and ln2, of y squared with respect to x. And just a real brief explanation. If you need a more fulfilling explanation, then you might want to look up on YouTube solids of revolution. But if we take this area below this curve, and we'll sort of understand what this curve is in a sec, but 1 plus cosh x, the hyperbolic cosine function, when we add 1 to it, we get a y-intercept of 2. If we take this region here between 0 and ln2, and then we rotate it around the axis, kind of looks like this, we get all of these cylinders, these very thin cylinders, and they all have a slight width of dx, and they all have a radius of the y value. So if you think about the volume of a cylinder, the volume of a cylinder is pi r squared h. Well, in this case, the radius is the y value of the curve, and the h value is the height of each cylinder, which we're calling the thin width dx. So each volume has each small volume, think of it maybe like a CD, and we've got a whole stack of them. So that's each small one is pi y squared dx, and if we integrate between two limits, we're adding up all of those volumes. So there's where the pi and the y squared dx comes from. But like I said, that's a very brief explanation of it. For more information, I recommend you look it up. Okay, so we're integrating this. This formula would be given to you normally in a problem like this, and therefore we need to go to the expression. And again, hyperbolic cosine is something unfamiliar to students unless you've done heaps of Schol papers. That's just e to the x plus e to the minus x over 2, so nothing nasty about that, except we need to square that expression, and that's where it's going to be an absolute mess to integrate. Although we could stick in hyperbolic cosine mode. So I'm going to do this problem using two different ways. The first way is to use the definition of the hyperbolic cosine. So we're integrating between 0 and ln2 of 1 plus, I'm just going to write a half instead, e to the x plus e to the minus x, all squared. Okay, and we square that, we get 1 plus 2 lots of the terms multiplied together, so that's just 2 times a half is 1, so we're going to e to the x plus e to the minus x, and then we're going to get the last thing, a quarter. The last thing squared is a quarter, e to the x all squared, so e to the 2x plus e to the minus 2x plus 2 lots of that thing there, squared, 2 lots of e to the x times e to the minus x is 1, so we're going to get 2 Okay, dx. Let me tidy this up a little bit. We've got 1 plus another half, so 3 over 2, plus e to the x, plus e to the minus x, plus a quarter e to the 2x, plus a quarter e to the minus 2x. Now we need to anti-diff that. Be careful when you're anti-diffing e to the minus x, it's e to the minus x divided by minus 1. And this one here is an eighth e to the 2x, this one's minus 1/8 e to the minus 2x, then ln2 and 0. Okay, and then we can sub in all of that information. ln2 makes a lot of these things simplify, because if we put ln2 into there, we get e to the ln2, which is just 2. Three over 2 ln2 plus 2. E to the minus ln2. E to the minus ln2. The minus can go at the top as 2 to the minus 1. And then the log and the e will cancel, so we get a half. 2 to the minus 1 is a half. So that's minus 1/2. Do the same thing with when we sub into this one. ln2 goes in for x, it's 2 ln2. The 2 goes up the top, so it's ln4, ln2 squared. So ln4 and the e to the ln4, so it's an eighth times 4. Your graphics calculator will work this all out for you anyways. So an eighth times 4 is a half. And then minus, I do the same thing, take the minus 2 up the top and you get a quarter. So it's minus an eighth times a quarter, which is minus 1 over 32. And that's when we sub in ln2, be careful with the 0 one. When we sub in the lower limit of 0, the first term disappears, but e to the 0 is 1. So we've got 1 minus 1, that cancels, and we've got an eighth times e to the 0, so an eighth minus an eighth. Okay, so everything goes to 0, that's cool. It doesn't always happen that way. Okay, and then if we tidy up all of this stuff, 1.5, or we'll leave it in exact form, how about that? So 2 minus a half plus a half, those are cancel. So 2 minus 1 over 32, which comes out to be 63 over 32. So 3 over 2 ln2 plus 63 over 32. Now, there is a different way of doing that, and it's if you knew a little bit more about hyperbolic cosines. So if we knew the definition, then we could just work with the definition, e to the x and so on. Where's the thing gone? But if you knew that when you take y is equal to 1 plus cosh x and we needed to square it, well, that's quite easy to square. We just get 1 plus 2 cosh x plus cosh x all squared, or cosh squared x. If you knew first up that the antiderivative of cosh x is just sine of x, or the hyperbolic sine function. So if we want to integrate sorry, that was y squared, and we're integrating this. So we've got x plus 2 hyperbolic sine of x. So that relationship is similar to how sine differentiates to cosine, and cosine differentiates to minus sine. Well, for hyperbolics, and you can check that out by looking at this definition there. So if we had y equals e to the, I'll ignore the 1. If we take this and we diff it, we get e to the x over 2 minus e to the minus x. So we get that, and that actually turns out to be the hyperbolic sine function. And if you differentiate that back, you get the hyperbolic cosine. So there's no plus or minus thing happening. And then the other thing is hyperbolic cosine squared. There's a trig identity that we can use for that. Sorry, this is a bit of a mess. But the hyperbolic sine function squared has a double angle formula, which is that. No, it's not. It's that. And then, again, you can derive that if you'd like to explore it. And then we anti-diff that. Remember that cosh goes back to shine. Well, it's spelt SINH, like it looks like cinch, but it's pronounced shine apparently. So we get a quarter hyperbolic sine of 2x, and then we get an extra half anti-diffed to be x over 2. And then we're subbing in same limit, 0 ln 2. Okay, so basically I'm showing you that you can do that if you knew some knowledge about how the hyperbolic functions worked in terms of trig identities, but you're not expected to know that unless you'd seen it before. So let's just go with the approach we did before, which has all the exponential functions in it, and we just anti-diff them like we do normally. And if you did do it this way, your calculator has the button, just like it has sin, cos and tan on it, or sine, cosine and tangent. It has got the hyperbolic functions in there. You just need to go through the option button on a Casio graphics calculator and search for it that way. I believe you have to press hype, F2 is hype, and you can see that the buttons are there. So from that point, once we've done the anti-differentiation, we can just sub in the limits and use our graphics calculator. Hopefully I haven't confused you with that last little bit there.